The question of how everything began from nothing isn't just a scientific puzzle. It's a profound philosophical mystery that forces us to contemplate the very essence of existence, as well as the origins of the universe. It challenges our understanding of reality, prompting us to ponder the moment when the universe was born, giving rise to the particles that form everything we know today. In our exploration, we delve into this question by examining the universe from the perspectives of particle physics and cosmology. Scientists employ mathematics and experiments in their attempts to tackle these monumental inquiries. Yet, beneath their scientific endeavors lies a deeper philosophical query. What does it truly mean for something to emerge from nothingness? How do the laws of physics account for the universe's emergence from a state devoid of space, time, and matter? Particle physics, a field that investigates the minuscule building blocks of the universe and the forces governing them, plays a pivotal role in this exploration. Unlike the objects we encounter in our daily lives, which abide by classical physics, the subatomic realm follows the principles of quantum mechanics, revealing a realm that is both captivating and counterintuitive. At the core of particle physics lies the quest to comprehend the fundamental constituents of the universe and the mechanisms underlying its functioning. Scientists within this discipline scrutinize particles such as quarks, electrons, and neutrinos, the elemental components of atoms, which in turn constitute matter. These particles are astonishingly tiny, challenging our conventional notions of space and time with their peculiar properties and behaviors. In the world of particle physics, a major milestone has been reached with the creation of the Standard Model. This theory outlines the fundamental forces and particles that form the universe, except for gravity. According to this model, there are four main forces: the electromagnetic force, responsible for electric and magnetic effects; the weak nuclear force, involved in radioactive decay; the strong nuclear force, binding quarks together in atoms' nuclei; and gravity, which, though not fully understood within this model, governs mass attraction. The Standard Model has proven highly successful in predicting and explaining particle behavior in numerous experiments. However, it's not the final answer. Scientists are on the lookout for a more comprehensive theory that includes gravity and addresses the enigmas of dark matter and dark energy. These substances, constituting most of the universe's mass and energy, remain challenging to detect directly. Advancing particle physics requires cutting-edge technology, like particle accelerators and detectors. These devices propel particles close to the speed of light and collide them, allowing scientists to observe resulting interactions and generated particles. The Large Hadron Collider in Geneva, Switzerland, stands as one of the world's most potent accelerators. It was here, in 2012, that scientists discovered the Higgs boson, a crucial particle in the Standard Model responsible for giving mass to other particles. This discovery marked a monumental leap in our understanding of particle physics. Despite its intricate nature, particle physics revolves around a fundamental question: what constructs the universe? This pursuit has led to groundbreaking discoveries and technologies like the World Wide Web, initially developed at CERN to facilitate global information exchange among scientists. As we venture deeper into the secrets of the cosmos, we uncover a fascinating overlap between cosmology and particle physics, a rich tapestry that spans from the vast expanse of space to the tiniest particles. Cosmology, focusing on the origin, structure, and evolution of the universe, finds an unexpected companion in particle physics, which delves into the basic building blocks of matter and the forces governing their interactions. Together, they offer new insights not only into what the universe is composed of, but also into its origins and its journey across billions of years. At the heart of this convergence lies the Big Bang theory, a pivotal concept in cosmology suggesting that the universe began around 13.8 billion years ago from an intensely hot and dense state, expanding ever since. Particle physics enriches our understanding of this early epoch by scrutinizing particle behavior at incredibly high energies, akin to those in the universe's first moments. For instance, scientists recreate primordial conditions on a smaller scale within immense particle accelerators like the Large Hadron Collider. Here they can observe reactions akin to those occurring shortly after the Big Bang. One captivating aspect of this partnership is the investigation into dark matter and dark energy, enigmatic substances constituting about 95% of the universe's total mass and energy. Dark matter is believed to consist of particles that neither emit nor reflect light, rendering them invisible and detectable solely through their gravitational effects. Conversely, dark energy is thought to drive the universe's accelerated expansion. Particle physicists are actively searching for dark matter particles, employing underground detectors and space-based observatories to hunt for signs of these elusive entities. Cosmologists integrate these discoveries into their models, refining their understanding of the universe's structure and dynamics. Moreover, the investigation into cosmic microwave background radiation, a remnant of the Big Bang, serves as a captivating example of how cosmology and particle physics merge. This radiation offers a glimpse of the universe when it was merely 380,000 years old, before stars and galaxies formed. By examining its subtle temperature fluctuations, scientists glean insights into matter distribution and the early universe's conditions. This informs theories in both cosmology and particle physics regarding the fundamental particles and forces present during the universe's birth. If you're still here, please like the video and turn on notifications for the channel so you don't miss out on our weekly astronomy documentaries. This interdisciplinary approach not only enriches our comprehension of the cosmos, but also challenges and refines theories in both realms. For instance, disparities in measurements of the Hubble constant, which depicts the universe's expansion rate, suggest potential new physics. Beyond the current standard model of particle physics, or the lambda CDM cosmological model. These anomalies drive the pursuit of a more comprehensive theory that harmonizes the laws governing the cosmos at both grand and minuscule scales. Expanding on the connection between cosmology and particle physics, it's vital to explore the fundamental forces of nature, which underpin both the vast cosmos and the subatomic realm. These forces serve as the universe's rulebook, governing interactions from galaxies to quarks. Understanding them sheds light on planetary motion and the stability of matter itself. Nature comprises four recognized fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each force plays a critical role in shaping the universe's structure and dynamics, influencing interactions across various scales and energies. Gravity is what keeps us grounded and dictates how planets, stars, and galaxies move. It's everywhere, yet it's the weakest of the four fundamental forces. Despite its weakness, gravity has a massive reach, holding the entire universe together. The strength of gravity between two objects depends on how much they weigh and how far apart they are, according to Isaac Newton's law of universal gravitation. Albert Einstein later refined our understanding of gravity with his theory of general relativity. He described gravity as the bending of space and time around massive objects. On the other hand, electromagnetism is the force behind most of the everyday phenomena we encounter. It's what makes electricity flow, magnets attract, and light travel. Electromagnetism is way stronger than gravity on a tiny scale, like between particles such as protons and electrons. It's crucial for the structure of atoms, the bonds between them, and even how signals move within our bodies. The strong nuclear force, also called the strong interaction, is the mightiest of the four forces, but it works over a very small distance. Its job is to keep protons and neutrons stuck together inside an atom's nucleus. If it weren't for the strong force, atoms wouldn't be the way they are now, because it beats the push away from each other that positively charged protons feel. It's also what keeps the tiny building blocks of protons and neutrons, called quarks, bonded together. On the other hand, the weak nuclear force, or weak interaction, handles tasks like radioactive decay and specific nuclear reactions, including those occurring in the sun. It operates over an even tinier range than the strong force. This force is essential in processes where one kind of subatomic particle transforms into another, like when a neutron changes into a proton, an electron, and a neutrino. This powerful force is essential in driving the nuclear fusion reactions that power stars, thus enabling the creation of elements across the universe. It's a key player in understanding both the vastness of cosmology and the intricacies of particle physics. Scientists are on a quest to formulate a unified theory that can seamlessly explain all four fundamental forces within a single framework, a challenge known as the theory of everything. Pursuing this theory is a driving force behind much of the ongoing research in physics, promising to unveil more of the universe's mysteries. Now, let's explore the fundamental particles that underpin the very essence of matter itself. These particles serve as the building blocks for everything we see and touch, from the air we breathe to the stars dotting the night sky. The Standard Model of particle physics offers a structured approach to identify the smallest constituents of matter, classifying them into quarks, leptons, and force carrier particles, which mediate the fundamental forces. Quarks, minute entities, combine to form protons and neutrons, the building blocks of atomic nuclei. There are 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. Due to a phenomenon called color confinement, quarks are never found alone in nature. They are always bound together in pairs or trios, forming particles known as mesons and baryons, respectively. For instance, protons consist of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. The strong nuclear force, the most potent of the 4 fundamental forces, governs the properties and interactions of quarks, keeping them tightly bound within the nucleus. Leptons, another set of fundamental particles, include the electron as its most familiar member. Similar to quarks, there are 6 different types or flavors of leptons: electron, muon, tau, and their respective neutrinos: electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, leptons don't feel the pull of the strong nuclear force. Electrons, for example, whirl around an atom's nucleus, playing vital roles in chemical reactions and electrical conductivity. Neutrinos are incredibly elusive particles that hardly interact with matter, which makes them exceptionally challenging to detect despite being produced abundantly by the sun and other nuclear processes. Aside from quarks and leptons, the Standard Model also includes force-carrying particles known as bosons, which oversee the 4 fundamental forces. Photons manage the electromagnetic force, gluons handle the strong force, W and Z bosons are in charge of the weak force, and the recently confirmed Higgs boson is associated with the Higgs field, responsible for giving particles their mass. Now, let's journey into the realm of the Big Bang theory, a pivotal concept providing a compelling explanation for how the universe began. This theory, a cornerstone of modern cosmology, offers insight into the universe's earliest moments, proposing that everything we see today, from tiny particles to immense galaxies, originated from an extraordinarily dense and hot point about 13.8 billion years ago. The Big Bang theory suggests that the universe was once compressed into an extremely hot and dense state, expanding rapidly thereafter. This expansion isn't like an explosion pushing matter outward into empty space, but rather it's the expansion of space itself. Picture a balloon with dots representing galaxies. As the balloon inflates, the dots move away from each other, illustrating how galaxies drift apart as the universe expands. Evidence supporting the Big Bang theory is abundant and compelling. One crucial piece of evidence supporting the Big Bang theory is the discovery of cosmic microwave background radiation, CMB, in 1965 by Arno Penzias and Robert Wilson. This faint glow exists throughout the universe and is essentially the afterglow of the Big Bang, but it has been stretched to microwave frequencies due to the universe's expansion. By studying the CMB, scientists gain valuable insights into the early conditions and composition of the universe. Another significant evidence is the observation of the redshift of galaxies. This means that as galaxies move away from us, the light they emit gets stretched to longer, redder wavelengths. Edwin Hubble first observed this in 1929, showing that the universe is not static, but constantly expanding. Quick reminder to subscribe if you haven't already, so you can keep up with our future astronomy documentaries. Thank you so much. Furthermore, the Big Bang theory helps explain the relative abundances of the lightest elements like hydrogen, helium, and lithium that we observe today. These elements formed shortly after the Big Bang in a process called nucleosynthesis, and their proportions match closely with what the theory predicts. However, despite the strong evidence, there are still mysteries surrounding the Big Bang theory. For instance, the nature of dark matter and dark energy, which make up the majority of the universe's mass-energy content, remains unknown. Additionally, the theory doesn't explain what happened before the Big Bang or the initial cause of the universe's expansion, leaving room for further exploration. Despite these unanswered questions, the Big Bang theory has revolutionized our understanding of the universe's origins, structure, and evolution. It presents a dynamic picture of the universe, beginning from an incredibly dense and hot state and evolving over billions of years into the diverse cosmos we see today. Immediately after the Big Bang, the universe was incredibly hot and dense, filled with energy. At this stage, normal matter like atoms and molecules couldn't exist. Instead, the universe was like a hot soup of its most basic components, quarks and gluons, which make up protons and neutrons, and the particles that hold them together. Think of it as a simmering pot of the universe's building blocks right after its explosive beginning. As the universe expanded, it began to cool down. Within a fraction of a second, it cooled enough for quarks to start sticking together, forming protons and neutrons, the building blocks of atoms. This phase, called the Hadron Epoch, was the first step towards creating the matter we know today. As it continued to cool, protons and neutrons began to combine, forming the first nuclei of atoms during a phase called nucleosynthesis, just a few minutes after the Big Bang. These early nuclei were mainly hydrogen, deuterium, a type of hydrogen with one extra neutron, helium, and a bit of lithium. The proportions of these light elements, as predicted by the Big Bang theory, match closely with what we see today, supporting the theory. However, it was still too hot for electrons to stick to these nuclei, preventing the formation of neutral atoms. It took about 380,000 years for the universe to cool down enough for electrons to finally join with nuclei, forming the first neutral atoms. This event, called recombination, was a turning point. It allowed light to travel freely for the first time, leading to the release of cosmic microwave background radiation, which gives us crucial evidence for the Big Bang. This shift from a hot soup to a universe filled with neutral atoms set the stage for the formation of stars, galaxies, and planets. Gravity began pulling matter together, forming clouds of gas that would eventually become the birthplaces of stars. These early stars played a key role in creating heavier elements through nuclear fusion in their cores, adding to the diversity of chemicals we see in the universe today. The Big Bang theory is supported by compelling evidence that not only confirms the idea of a universe born from an incredibly dense and hot state, but also sheds light on its evolution over billions of years. This evidence is essential for scientists and the public alike, providing a coherent explanation of cosmic history grounded in careful observation and analysis. A cornerstone of this evidence is the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is a faint glow spread throughout the universe, lingering from the early moments after the Big Bang. Over time, the universe's expansion has cooled this radiation to microwave frequencies. By studying the CMB using satellites like COBE, WMAP, and Planck, scientists have obtained a detailed picture of the universe's infancy, revealing subtle temperature differences that correspond to variations in density. These variations were the starting points for the formation of all cosmic structures we see today, including galaxies, stars, and planets. Additionally, the expansion of the universe itself serves as direct evidence supporting the Big Bang theory. In the 1920s, Edwin Hubble made a significant discovery. Galaxies are moving away from us in all directions, and their speed increases with their distance from us. This discovery, known as Hubble's law, suggests that the universe is expanding uniformly. It implies that in the past, the universe must have been much smaller, hotter, and denser, a concept consistent with the Big Bang theory. This expansion is a dynamic reminder of the universe's explosive beginning. Another important piece of evidence comes from the abundance of light elements. According to the Big Bang theory, hydrogen, helium, and a bit of lithium were formed during the first few minutes after the Big Bang in a process called primordial nucleosynthesis. Observations of the amounts of these elements in the universe closely match what the theory predicts. This similarity supports the idea that the universe was once in a hot, dense state, which was necessary for the formation of these elements. Furthermore, the structure of the universe on a large scale, seen through the distribution of galaxies and galaxy clusters, also supports the Big Bang theory. Galaxies are not scattered randomly, but instead form a vast, interconnected web of filaments and voids. This structure aligns with the gravitational growth of small density fluctuations in the early universe, as predicted by the Big Bang theory. Now let's explore the concept of quantum fluctuations, a phenomenon deeply rooted in the quantum realm that plays a crucial role in shaping the cosmos. Quantum fluctuations refer to temporary changes in the amount of energy at a specific point in space. They are governed by Werner Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be precisely measured at the same time. This principle introduces the idea of inherent uncertainty at the quantum level and is fundamental to our understanding of quantum mechanics. In space, where it might seem like there's nothing, there's actually a lot happening at a tiny scale. Even in seemingly empty space, there are tiny, fleeting events called quantum fluctuations. These fluctuations involve the sudden appearance of particle-antiparticle pairs, known as virtual particles, which exist for an incredibly short time before vanishing. Although these virtual particles don't stick around for long, they still have a real impact. They can affect the behavior of other particles, causing subtle changes like shifts in the energy levels of electrons in atoms. Scientists have observed and confirmed these effects through experiments. But quantum fluctuations aren't just a curious phenomenon. They're also believed to have played a crucial role in shaping the universe. During cosmic inflation, a rapid expansion phase shortly after the Big Bang, these fluctuations were stretched across vast distances. This stretching process amplified the tiny variations in the density of matter, ultimately leading to the formation of large-scale structures like galaxies and galaxy clusters. The patterns we see in the cosmic microwave background radiation are direct evidence of these quantum fluctuations, providing insight into the universe's early days. At the core of quantum fluctuations is the Heisenberg uncertainty principle, which suggests that certain pairs of physical properties can't be precisely measured simultaneously. This principle implies that even in what appears to be empty space, there's a constant flux of virtual particles popping in and out of existence. These particles are dubbed virtual because they can't be directly seen. They exist briefly, borrowing energy from the vacuum to pop into existence before quickly annihilating each other and giving back the borrowed energy. However, in specific situations, these quantum fluctuations can trigger the creation of actual particles. One such circumstance occurs near a black hole's event horizon, a phenomenon called Hawking radiation. Stephen Hawking suggested that quantum fluctuations near the edge of a black hole could generate pairs of particles and antiparticles, with one member of the pair being pulled into the black hole while the other escapes into space. This process effectively generates real particles from the vacuum, causing the black hole to lose mass over time due to this radiation. Another instance where quantum fluctuations result in particle creation is during cosmic inflation, a theory proposing that the universe rapidly expanded shortly after the Big Bang. During inflation, quantum fluctuations were stretched across large distances, enhancing their effects. These fluctuations in the early universe's density acted as the starting points for the formation of all the large-scale structures we see today, like galaxies and galaxy clusters. The amplification of quantum fluctuations during inflation suggests that the virtual particles could become frozen into real particles, adding to the universe's material makeup. This process of creating particles from quantum fluctuations highlights how intertwined quantum mechanics and cosmology are, revealing the quantum roots of cosmic change. This explanation delves into how phenomena occurring at the tiniest scales can significantly impact the behavior of the universe on its grandest scales, blurring the boundaries between what we perceive as nothingness and the tangible world around us. By exploring the quantum realm, we uncover the crucial role energy plays in forming particles, essentially bridging the gap between fleeting quantum fluctuations and the solid reality of our universe. At the heart of this process lies one of the most renowned equations in physics, E equals mc squared, proposed by Albert Einstein. This equation highlights the interchangeability of energy, E, and mass, m, with c representing the speed of light. It fundamentally illustrates how energy acts as a catalyst, transforming the potential stored within quantum fluctuations into the actual building blocks of the cosmos. In the seemingly empty vacuum of space, there exists a hidden frenzy of activity due to quantum fluctuations. These fluctuations represent temporary changes in energy at specific points in space, allowing for the creation of particle-antiparticle pairs. Although these pairs typically annihilate each other almost instantly, returning the borrowed energy to the vacuum under certain conditions, they can manifest as real particles. This process of converting energy into particles is crucial for understanding the early universe and the mechanisms that led to its abundant matter. Following the Big Bang, the universe was initially a hot, dense soup of energy. As it expanded and cooled, some of this energy condensed into particles, adhering to the principles laid out by Einstein's equation. This led to various phases in the early universe, including the electroweak epoch and the quark epoch, where fundamental forces of nature separated and the elemental particles grouped together to form the protons and neutrons constituting atomic nuclei today. Energy isn't just a force, it's a key player in the creation and interaction of particles as well as the structures they form. Take the nuclear fusion processes in stars, for example. The energy released during these processes synthesizes heavier elements like carbon and iron, which are essential for life. This shows how energy from sparking stars to crafting elements plays a crucial role in shaping our universe. When we delve into the importance of energy in particle formation, we encounter another fundamental concept, the Heisenberg uncertainty principle. This principle isn't just a complex mathematical idea, it sheds light on the inherent uncertainty of the quantum world and directly affects how particles come into existence. Put forth by Werner Heisenberg in 1927, the principle states that we can't know both the exact position and momentum of a particle simultaneously. This uncertainty isn't a flaw in our measurements, but a fundamental aspect of the quantum realm. The uncertainty principle is closely linked to particle creation, especially regarding quantum fluctuations in the vacuum of space. According to quantum field theory, space isn't truly empty. It's filled with virtual particles that pop in and out of existence. These particles are called virtual, because they only exist temporarily, borrowing energy from the vacuum due to the allowances made by the uncertainty principle. The Heisenberg uncertainty principle allows for temporary fluctuations in energy, essentially permitting a brief borrowing of energy from the vacuum of space. However, this borrowed energy must be quickly repaid, preventing any noticeable violation of energy conservation. This temporary energy borrowing enables the spontaneous formation of pairs of particles and their corresponding antiparticles. Typically, these pairs annihilate each other almost instantly, returning the borrowed energy to the vacuum. However, their brief existence is a direct result of the uncertainty regarding their positions and momenta. Under specific extreme circumstances, such as near a black hole's event horizon, or during the rapid expansion of the early universe, these virtual particles can become separated and transform into real, observable particles. This process, known as particle creation from the vacuum, showcases the essential role of the uncertainty principle in the intricate dynamics of the quantum realm and the structure of the universe. During the initial moments after the Big Bang, the universe was too hot and dense for particles or atoms to form. Instead, it existed in a state called quark-gluon plasma. This state featured quarks, which are fundamental particles that later combine to form protons and neutrons, freely moving within a sea of gluons, particles that bind quarks together through the strong force. As the universe expanded and cooled, it reached a point where quarks could come together to form protons and neutrons, which are the basic constituents of atomic nuclei. This phase, known as the Hadron epoch, took place within the first microsecond to 1 second after the Big Bang. The emergence of protons and neutrons marked a significant milestone in the early universe, laying the groundwork for the development of more complex forms of matter. After the Hadron epoch, as the universe continued to cool, it entered what's known as the lepton epoch, lasting from about 1 second to a few minutes after the Big Bang. During this phase, leptons like electrons were the main form of matter. However, it was still too hot for protons and neutrons to join with these electrons to form nuclei. The pivotal moment in particle formation followed shortly after, nucleosynthesis. This process occurred within the first few minutes post-Big Bang, when the universe had cooled down sufficiently for protons and neutrons to start merging and forming the nuclei of the simplest elements, primarily hydrogen and helium, with small amounts of lithium and beryllium. This early nucleosynthesis played a crucial role in producing most of the helium in the universe, along with the hydrogen that hadn't combined into helium nuclei yet. It's worth noting that at this stage these weren't complete atoms as we know them today, with electrons orbiting nuclei. The universe remained too hot for electrons to be captured into orbits around nuclei, preventing the formation of neutral atoms. The formation of neutral atoms, called recombination, didn't occur until around 380,000 years after the Big Bang. This event led to the separation of matter and radiation, and the release of cosmic microwave background radiation. This radiation, often referred to as the afterglow of the Big Bang, offers us a snapshot of what the universe looked like at that early stage. Let's delve into a captivating period when the fundamental forces of nature began to take shape, defining the evolving cosmos. This process of separation is crucial for understanding how the universe developed from its earliest moments to the structured expanse we see today. Initially, in the universe's infancy, all forces existed as one unified force, reflecting the extreme conditions of high temperature and density. As the universe expanded and cooled, this unified force began to break apart into distinct forces we now know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity was the first force to break away, becoming distinct as the universe cooled from its incredibly hot and dense state. This separation likely occurred just a fraction of a second after the Big Bang, marking a significant step in the universe's journey toward the complex interactions we see today. Gravity's emergence laid the groundwork for the formation of galaxies, stars, and planets, shaping the structure of the universe as we know it. After gravity's separation, the grand unified force, which combined electromagnetism, the strong nuclear force, and the weak nuclear force, remained unified until further cooling occurred. As temperatures dropped, the strong nuclear force, responsible for binding quarks within protons and neutrons and maintaining the stability of atomic nuclei, separated from the electro-weak force, which combined electromagnetism with the weak nuclear force. Around 10 circumflex 36 to 10 circumflex 32 seconds after the Big Bang, during a phase known as cosmic inflation, there was a crucial separation that paved the way for the creation of the universe's first particles. Initially, the electro-weak force governed the universe's energetic landscape until it experienced its own symmetry breaking. This occurred approximately 10 circumflex 12 seconds after the Big Bang, when the electro-weak force split into two distinct forces: the electromagnetic force carried by photons and the weak nuclear force, responsible for processes like radioactive decay and nuclear fusion in stars. This separation finalized the lineup of fundamental forces, allowing the universe to continue cooling down and giving rise to more intricate particles and eventually atoms. The separation of these fundamental forces during the universe's early stages played a crucial role in enabling the diverse array of matter and structures we observe in the cosmos today. Moving forward from these pivotal moments of force separation, we explore the significance of the electro-weak epoch. This epoch, occurring shortly after the Big Bang, marked a significant phase where the electromagnetic and weak nuclear forces, two of the universe's four fundamental forces, were unified as one force called the electro-weak force. Taking place approximately between 10 circumflex 12 seconds and 10 circumflex 6 seconds after the Big Bang, during a time of cooling but still high energy, the electro-weak epoch played a vital role in shaping the early universe and laying the groundwork for the formation of matter as we know it. In the early stages of the universe, it was filled with a dense mix of tiny particles called quarks, leptons, and their opposites, as well as special particles known as electroweak bosons, which controlled a unified force. As the universe expanded and cooled down, it hit a critical temperature. At this point, something significant happened. The electroweak force experienced what's called a symmetry-breaking event. This event caused a split between two important forces: the electromagnetic force, which is responsible for things like light and electricity and is controlled by particles called photons, and the weak nuclear force, which governs certain types of radioactive decay and is controlled by particles known as W and Z bosons. This split was crucial for the universe to develop further because it allowed for a wider range of interactions. Eventually, these interactions led to the formation of atoms and the structure of everything we see in the cosmos. This period, known as the electroweak epoch, is hugely significant in our understanding of particle physics and the Standard Model. During this time, something called the Higgs mechanism came into play. This mechanism, related to the Higgs field, played a vital role. It gave particles their mass, which was a key part of the event that separated the electromagnetic and weak nuclear forces. The discovery of the Higgs boson in 2012, a particle associated with the Higgs field, provided strong evidence supporting our theories about the electroweak force and its importance. Quarks, which are the basic building blocks of matter, are also influenced by the strong nuclear force, one of the four fundamental forces. This force, sometimes called the strong interaction, is incredibly powerful but only acts over very short distances. In the earliest moments of the universe, a force called the strong nuclear force played a crucial role. It acted like a glue, binding together tiny particles called quarks to form groups. These groups of quarks, called baryons, are what make up protons and neutrons, which are essential for building atomic nuclei. This process began when the universe cooled down enough for the strong force to become stronger than the energy that was keeping quarks apart. In this still very hot environment, quarks started to interact more closely, forming pairs called quark-antiquark pairs, and groups of three that would eventually become protons and neutrons. Protons are made up of two up quarks and one down quark, while neutrons consist of two down quarks and one up quark. The specific combination of quarks determines the properties of these particles, such as their charge. Protons have a positive charge due to their quark makeup, while neutrons are electrically neutral. This phase of the universe's development wasn't just about forming these particles, but also about transitioning from a state where quarks could move around freely, known as a quark-gluon plasma, to a state where they were locked within protons and neutrons. This locking mechanism is vital for the stability of matter as we know it. Without it, the complex structures of the universe, from atoms to galaxies, couldn't exist. The transformation of quarks into protons and neutrons set the stage for the next phase of cosmic evolution, the era of nucleosynthesis, when the first atomic nuclei were formed. These early stages of matter coming together from fundamental forces and particles influenced by the conditions of the early universe are crucial for understanding the history of the cosmos and the very substance that surrounds us. As the universe expanded and cooled following the Big Bang, there came a crucial point where the temperature allowed protons and neutrons to fuse. This happened about 3 minutes after the Big Bang. At this time, the nuclear forces became strong enough to overcome the repulsion between positively charged protons, allowing them to merge with neutrons and create the nuclei of the simplest elements. Mostly, hydrogen nuclei fused to form helium, along with small amounts of deuterium, tritium, and trace quantities of lithium and beryllium. This process, known as nucleosynthesis, holds great importance. Firstly, it determined the initial abundance of light elements in the universe. The proportions of hydrogen and helium formed during this period match closely with what we observe in the universe today, providing strong evidence for the Big Bang theory. Secondly, nucleosynthesis paved the way for star formation. Stars, through their own nuclear fusion processes, later produced heavier elements necessary for life and the universe's intricate structures. Nucleosynthesis is not merely about creating atomic nuclei. It signifies the universe's shift from simple particles to a diverse range of matter. This marked the beginning of chemical diversity, laying the foundation for the universe's evolution, leading to the formation of planets, life, and the myriad celestial phenomena. Moving forward in our exploration, we encounter another significant event, the formation of the first atoms. This occurred roughly 380,000 years after the Big Bang, as the universe cooled to a point where electrons could bind with nuclei to form neutral atoms, a process called recombination. This marked the emergence of atomic matter as we recognize it today, against the backdrop of an expanding and cooling universe from its initial state of extreme heat and density. As the universe cooled down, protons and neutrons formed from smaller particles called quarks began to interact through a process called nuclear fusion. This process, known as nucleosynthesis, was crucial in creating the first simple atomic nuclei. It mainly resulted in the formation of hydrogen, which is basically just a single proton, and helium nuclei, along with small amounts of deuterium, heavy hydrogen, and lithium. These light elements determined the initial chemical composition of the universe, making it rich in hydrogen and helium, the most basic elements found throughout the cosmos. However, during this time, the universe was still too hot for electrons to remain attached to these nuclei. Instead, they circulated freely, creating a state known as free electron plasma, which scattered photons and prevented the universe from becoming transparent. As the universe expanded and cooled further, it eventually reached a temperature where photons didn't have enough energy to break apart hydrogen atoms. This allowed electrons to combine with hydrogen and helium nuclei, forming the first stable atoms. This process, called recombination, significantly reduced photon scattering, leading to the universe becoming transparent for the first time. The photons released during this event now form what we observe as the cosmic microwave background radiation, providing a snapshot of the universe at the moment of recombination. The formation of these first stable atoms marked a pivotal moment in the universe's story. It signaled the transition from a hot, dense state to a cooler, more structured one, capable of supporting complex formations like stars and galaxies. This event ended the universe's dark ages, a period before the first stars ignited, and set the stage for the gravitational collapse of matter, ultimately leading to the formation of stars and galaxies. Stars play a crucial role in enriching the universe with essential elements needed for planets and life. This enrichment process, called stellar nucleosynthesis, is responsible for creating the diverse array of elements we observe today. Initially, after the Big Bang, the universe consisted mainly of hydrogen and helium. However, the complexity of life and the world around us requires a much wider range of elements. Stellar nucleosynthesis acted as a cosmic furnace, transforming the simple elements of the early universe into a rich variety of chemical elements. Nucleosynthesis occurs in various stages and environments. The first stage, known as Big Bang nucleosynthesis, happened within minutes of the universe's birth, producing light elements like hydrogen, helium, and trace amounts of lithium and beryllium. However, this process couldn't create the heavier elements crucial for life. The next phase occurred within stars. Stars serve as factories for element production, fusing lighter elements into heavier ones through nuclear fusion in their cores. Hydrogen burning starts the process, converting hydrogen nuclei into helium. As stars evolve, they fuse helium into heavier elements like carbon, oxygen, and up to iron through successive stages of nuclear burning such as carbon burning, neon burning, oxygen burning, and silicon burning. This process ultimately seeds the universe with the necessary ingredients for life and cosmic structure. Creating elements heavier than iron involves processes different from those in stellar cores due to their energy requirements. These elements cannot be formed through fusion under normal circumstances. Instead, the R process, rapid neutron capture, and the S process, slow neutron capture, take over, mainly during supernova explosions and in the outer shells of asymptotic giant branch, AGB stars. Supernovae, which are massive star explosions, create conditions suitable for the R process. Here, atomic nuclei absorb a dense flux of neutrons, leading to the formation of many heavier elements in the periodic table. The S process, on the other hand, occurs in the calmer surroundings of AGB stars, where neutrons are captured more slowly, allowing for the creation of elements like barium and lead. The diverse elements produced by nucleosynthesis are dispersed throughout the galaxy by stellar winds and supernova explosions. They seed interstellar clouds with materials necessary for the formation of the next generation of stars, planets, and ultimately, life. This cycle of star formation, nucleosynthesis, and death, followed by the birth of new stellar systems, has enriched the universe with complex chemistry over billions of years. Particle accelerators are advanced machines designed to propel charged particles like protons or electrons to incredibly high speeds and then collide them together or against targets. This process creates conditions similar to those immediately after the Big Bang. These sophisticated tools are pivotal for scientists as they delve into the fundamental properties of matter and the forces governing particle interactions. By accelerating particles to nearly the speed of light and causing them to collide, particle accelerators help researchers dismantle atomic components into their basic constituents. This reveals particles and phenomena that are otherwise invisible under normal circumstances. The operation of a particle accelerator involves using electric fields to speed up particles and magnetic fields to guide and focus them along a predefined path. This path can either be circular, as seen in synchrotrons and storage rings, or linear, as in linear accelerators, linacs. When these highly energized particles collide, they give rise to a plethora of new particles. This allows scientists to explore the rules of particle physics in environments with extremely high energy densities, reminiscent of the conditions just after the Big Bang. Particle accelerators come in various types, each with its own role in research and beyond. Take the Large Hadron Collider, LHC, at CERN, Switzerland, for example. It's the biggest and most powerful accelerator globally, built to explore profound questions about the universe like the Higgs boson and dark matter. But these accelerators aren't just for pure science, they have practical applications too. In medicine, they're crucial for cancer treatment and making isotopes for medical scans. Industries use them for making materials and semiconductors, while they help in art and archaeology by analyzing artifacts without harm. Building and running these machines is a marvel of engineering and physics. They use cutting-edge tech like superconducting magnets and precise particle detectors. Beyond discovery, they push technological boundaries, impacting various fields and society's technological progress. These accelerators have significantly deepened our knowledge of the universe. By speeding up particles and causing collisions, they've unveiled particles and forces fundamental to everything we see around us. Particle accelerators have led to groundbreaking discoveries, such as pinpointing the Higgs boson. In 2012, scientists at CERN's Large Hadron Collider, LHC, announced they had spotted a particle matching the Higgs boson, often dubbed the God particle. This particle, anticipated by the standard model of particle physics, is key to explaining why other particles possess mass. Its discovery was a pivotal moment in particle physics, affirming a vital aspect of the standard model and contributing to the 2013 Nobel Prize in Physics for François Englert and Peter Higgs. Moreover, accelerators played a crucial role in confirming the existence of quarks, the tiny units forming protons and neutrons. In the late 1960s and early 1970s, experiments at the Stanford Linear Accelerator Center, SLAC, provided the first tangible proof of quarks, backing the quark model proposed by physicists Murray Gell-Mann and George Zweig in the 1960s. This significantly advanced our comprehension of matter's structure, establishing quarks as fundamental constituents. Additionally, accelerators have enabled the exploration of antimatter, which mirrors matter but carries opposite charge. Studies at CERN and elsewhere have allowed physicists to produce, confine, and scrutinize antimatter particles like antihydrogen. These inquiries are critical for testing fundamental symmetries of the universe and comprehending why the cosmos primarily consists of matter, despite the Big Bang theory foreseeing equal quantities of matter and antimatter. Particle accelerators have played a crucial role in discovering numerous subatomic particles like W and Z bosons, which facilitate the weak nuclear force responsible for radioactive decay. Discovered in the 1980s at CERN, these particles provided essential evidence for the electroweak theory. This theory unites electromagnetic and weak forces, marking a significant milestone in the pursuit of a unified theory of fundamental forces. Besides these fundamental breakthroughs, particle accelerators have also fueled advancements in medical treatments, such as cancer therapy using particle beams, and in technologies like the World Wide Web, initially developed at CERN to streamline information sharing among scientists. But how do these experiments in particle physics confirm theoretical predictions? It's a collaborative effort between theorists and experimentalists. Theoretical physicists craft models grounded in mathematical principles to explain particle properties and behaviors, as well as the forces governing their interactions. These models often make precise predictions about interaction outcomes or the existence of unseen particles. To put these predictions to the test, experimental physicists utilize particle accelerators. These machines ramp up particles to high energies and smash them together, creating conditions where unusual phenomena become observable. Detectors surrounding the collision points capture and log the particles generated, and sophisticated data analysis techniques are employed to decode the results. Validating theoretical predictions involves confirming them through experimental results. In particle physics, this means conducting experiments in various locations worldwide to observe the same phenomena under similar conditions. This process adds credibility to the findings, ensuring they are not chance occurrences or influenced by experimental variables. The Standard Model of particle physics is a theory that explains 3 of the 4 fundamental forces in the universe: electromagnetic, weak and strong nuclear forces, and classifies all known elementary particles. It has been developed over decades through global collaboration among physicists, merging quantum mechanics and special relativity into a unified framework called quantum field theory. The model divides elementary particles into fermions, matter's building blocks like quarks and leptons, and bosons, force carrier particles such as photons and gluons. A significant achievement of the Standard Model was the prediction and discovery of the Higgs boson in 2012 at the Large Hadron Collider. This particle, through the Higgs mechanism, gives mass to other particles, filling a crucial gap in the model and confirming the existence of the Higgs field and its associated particle. Despite its notable achievements, the Standard Model of particle physics doesn't cover everything. It doesn't include gravity, the 4th fundamental force described by general relativity. It also doesn't address dark matter and dark energy, which seem to make up most of the universe's mass and energy. Moreover, the model can't predict the masses of elementary particles or incorporate gravity, indicating that there's likely a more comprehensive theory yet to be found. While the Standard Model has been successful in explaining many phenomena, it has its limits, showing where our understanding of the universe falls short. These limitations indicate areas where we need to delve deeper into physics to uncover a more complete theory of fundamental forces and particles. One major limitation is the model's inability to account for gravity. Gravity, as described by Einstein's general relativity, is crucial for understanding how the cosmos behaves on a large scale, from planetary orbits to the evolution of galaxies and the universe itself. However, the Standard Model relies on quantum field theory, which doesn't naturally include gravity. This disparity between theories of the very big, general relativity, and the very small, quantum mechanics, remains a significant challenge in physics. The Standard Model faces several limitations, notably its inability to shed light on dark matter and dark energy. Observations suggest that a large part of the universe, about 85%, is dark matter, which doesn't emit, absorb, or reflect light and is only detectable through its gravitational influence. Dark energy, contributing to roughly 68% of the universe's total energy, is believed to drive its accelerating expansion. However, the Standard Model doesn't predict dark matter particles or explain the properties of dark energy, leaving a significant portion of the universe unexplained. Another puzzle the Standard Model can't solve is the matter-antimatter imbalance in the universe. According to the model, the Big Bang should have produced equal amounts of both, resulting in their mutual annihilation and leaving behind radiation. Yet the universe is predominantly made of matter, indicating that processes beyond the model's scope favored matter over antimatter. Additionally, the Standard Model initially assumed neutrinos were massless, but experiments have shown otherwise, presenting a challenge to the model's understanding. These discoveries have prompted revisions to the model and raised questions about the origins of neutrino mass and their role in the cosmos. The Standard Model lacks a unifying principle that could explain the existence of its particles and forces. Thus, physicists continue to seek a theory of everything that would unify all fundamental forces, including gravity, providing a deeper understanding of particles and their interactions. Looking beyond the Standard Model, dark matter and dark energy remain profound mysteries in cosmology, comprising about 95% of the universe's total mass-energy content. Dark matter accounts for roughly 27%, while dark energy makes up approximately 68%, with ordinary matter, visible and interactive, constituting only a small fraction. Despite being invisible and undetectable conventionally, their gravitational effects hint at their existence and influence on the universe's expansion. Dark matter is a mysterious substance that doesn't interact with light, making it invisible to traditional telescopes and extremely hard to directly observe. Its existence was proposed by Fritz Zwicky in the 1930s, when he noticed that galaxies in clusters moved faster than expected based on visible matter alone. Evidence from various observations, such as galaxy rotation curves and gravitational lensing, has since supported the idea of dark matter. Even though it can't be seen, dark matter affects the universe through gravitational forces, shaping the formation of galaxies and galaxy clusters. It acts as a sort of framework around which visible matter gathers, forming the large-scale structures we see. Dark energy, on the other hand, is a puzzling force causing the universe to expand at an increasing rate. Its discovery in the late 1990s surprised astronomers who anticipated the universe's expansion to be slowing down due to gravity. Instead, observations revealed the opposite, galaxies moving away from each other faster over time. Dark energy is believed to be present everywhere in space, not thinning out as the universe expands. Its nature is even more enigmatic than dark matter, challenging our understanding of physics as it doesn't neatly fit into existing theories like the Standard Model or general relativity. Dark matter, comprising roughly 27% of the universe, interacts with ordinary matter solely through gravity. Unlike visible matter, it neither emits nor reflects light, making it invisible and detectable only through its gravitational influence. We infer its presence from its gravitational pull on galaxies and clusters, affecting their rotation and distribution. Dark matter essentially serves as a cosmic scaffold, providing the gravitational structure necessary for the formation and clustering of galaxies. In the early universe, dark matter's gravitational pull amplified tiny irregularities left by quantum fluctuations, leading to the creation of large-scale structures like galaxies and galaxy clusters. These structures provided the conditions for ordinary matter to gather and cool, initiating star formation and the synthesis of heavier elements within stars. Dark energy, constituting approximately 68% of the universe, drives its accelerated expansion. Unlike dark matter, it's evenly spread throughout space and exerts a repulsive force countering gravity. Its precise nature remains a major puzzle in physics, but its impact on the universe's expansion rate profoundly influences particle formation and cosmic evolution. This accelerated expansion affects the universe's density, temperature, and the rate at which structures form and evolve over time. This expansion also influences the cooling of the universe and the regions where particles come together to form atoms, molecules, stars, and galaxies. Supersymmetry, SUSY, is a theoretical framework proposing a symmetry between two fundamental particle classes: bosons, which carry forces, and fermions, which make up matter. According to SUSY, each boson in the Standard Model has a corresponding fermion partner, and vice versa, although these partners have not yet been observed. Superpartners are hypothetical particles that complement those in the Standard Model of particle physics. They have names similar to Standard Model particles like squarks for quark superpartners and selectrons for electron superpartners. Supersymmetry, or SUSY for short, aims to solve unresolved issues in physics, like the hierarchy problem, which deals with the vast difference in the strength of gravitational force compared to other fundamental forces. According to SUSY, new symmetries in physics can stabilize the mass of the Higgs boson, explaining why it's not much heavier. This theory also suggests that supersymmetric particles, particularly the lightest one called the LSP, could be stable, weakly interacting, and electrically neutral, qualities that make them promising candidates for dark matter, which makes up about 27% of the universe. Despite SUSY's elegant theoretical foundation and its potential to solve big mysteries in physics, like dark matter, we haven't found direct evidence for it yet. Scientists have searched for superpartners using particle accelerators like the Large Hadron Collider, LHC, at CERN, but haven't had success so far. This has led to tighter constraints on SUSY models and pushed the predicted masses of superpartners beyond what current experiments can detect. Have you ever wondered if there are particles beyond what we already know in the standard model? Well, there are indeed some fascinating theories suggesting just that. These theories seek to tackle the limitations and unanswered questions left by the standard model, such as mysteries surrounding dark matter, the hierarchy problem, and the quest to unify fundamental forces. One of the key theories in this realm is supersymmetry, SUSY, which expands upon the standard model by introducing a superpartner for each known particle. These superpartners haven't been observed yet, but if they exist, they could potentially shed light on the enigmatic nature of dark matter and help stabilize the mass of the Higgs boson, addressing the hierarchy problem. Supersymmetry predicts a whole array of new particles, like the gluino, partner to the gluon, and the gravitino, partner to the hypothetical graviton associated with gravity. Another significant theory is string theory, which suggests that particles aren't tiny dots but rather vibrating strings. These strings have different vibration patterns corresponding to various particles, potentially providing a unified explanation for all fundamental forces, including gravity. String theory also hints at the existence of extra spatial dimensions beyond the familiar three. Theories involving extra dimensions, seen in various string theory formulations and concepts like the brain world scenario, propose that our universe might possess more than just the three dimensions we typically perceive. These theories offer intriguing possibilities for understanding the fundamental nature of our universe and the particles within it. In the realm of theoretical physics, there's a concept suggesting that there may be extra dimensions beyond the ones we're familiar with, but they could be incredibly tiny, making them undetectable by our current experimental methods. These extra dimensions, if they exist, might help explain why gravity seems so much weaker compared to other fundamental forces like electromagnetism or the strong and weak nuclear forces. They could also imply the existence of particles associated with these dimensions. One approach to exploring these ideas involves theories aiming to unify the fundamental forces into a single overarching force. These theories predict the existence of new particles, like heavy gauge bosons, which could facilitate transitions between different types of particles. For instance, they might enable transformations between quarks and leptons. Although these theories are elegant mathematically and offer promising solutions to some gaps in our current understanding, such as those within the standard model of particle physics, we haven't yet found direct experimental evidence supporting the existence of these hypothesized particles. Particle accelerators like the Large Hadron Collider are actively exploring this frontier, searching for signs of these elusive particles. Discovering them would not only confirm these theories, but also revolutionize our comprehension of the universe's fundamental structure and forces. Now, let's shift our focus to gravity's role in particle formation. Despite being the weakest of the fundamental forces, gravity has a significant impact on the formation of particles and the evolution of the universe. This influence is most apparent in processes like star formation. As massive clouds of gas and dust collapse under gravity's pull, they create conditions ripe for nuclear fusion in their cores. This fusion process, which converts hydrogen into helium, not only powers stars, but also generates heavier elements crucial for life and the diversity of elements found throughout the cosmos. Gravity plays a crucial role in the creation of black holes, which are areas in space where gravity is incredibly intense, trapping everything, including light. Near the edge of a black hole, called the event horizon, extreme conditions occur. According to theories like Hawking radiation, pairs of particles and their antiparticles can spontaneously appear from the empty space surrounding the black hole. One particle falls into the black hole while the other escapes, hinting at a fascinating relationship between gravity and quantum mechanics, influencing how particles are formed. Gravity's impact on particle formation extends to the entire universe. The way matter is spread out, from the thin strands forming the cosmic web to the creation of galaxies and clusters, is all dictated by gravity. This distribution determines where particles gather to form stars, planets, and other celestial bodies. While other forces like electromagnetism and nuclear forces dominate at smaller scales, gravity's influence over cosmic distances and time periods is essential for understanding how the universe changes over time. Everything from the formation of particles to galaxies is evidence of gravity shaping the universe since its earliest days. The theory of inflation, introduced by physicists like Alan Guth and Andrei Linde in the early 1980s, is a crucial concept in cosmology. It suggests that the universe went through a rapid and exponential expansion in the first moments after the Big Bang. This expansion, much faster than the speed of light, rapidly increased the size of the universe. Inflation addresses several problems in the Big Bang theory, such as the horizon problem. This problem questions how distant parts of the universe ended up having the same temperature when light hasn't had enough time to travel between them since the universe began. Inflation theory proposes that regions of the universe, which now appear distant and disconnected, were actually close together in the early stages after the Big Bang. As the universe rapidly expanded, these regions were driven apart, but they had enough time to reach thermal equilibrium, sharing the same temperature, before they were separated beyond the reach of any causal connection. This addresses the horizon problem, which puzzled scientists because distant parts of the universe seem to have the same temperature, despite not having enough time to interact with each other. Another puzzle inflation theory tackles is the flatness problem. Observations show that the universe appears remarkably flat on large scales, following the rules of Euclidean geometry. This flatness would require precise initial conditions if the universe expanded steadily from the Big Bang. Inflation elegantly solves this by stretching out any curvature in the fabric of the early universe, resulting in a universe that appears flat on large scales. Furthermore, inflation explains how the large-scale structure of the universe, such as galaxies and galaxy clusters, formed. It suggests that tiny quantum fluctuations in the early universe were stretched to enormous scales during the inflationary period. These fluctuations then acted as seeds for the formation of structures through gravitational attraction. Observations of the cosmic microwave background radiation, the lingering glow of the Big Bang, support inflation theory. The patterns of slight temperature variations in the CMB match the predictions of inflation, reinforcing its status as a key component of our understanding of the early universe. However, inflation theory also brings forth new questions, such as what triggered inflation to begin and what caused it to end. Various models, drawing from concepts in quantum field theory and string theory, aim to provide a more comprehensive explanation for these dynamics. In terms of explaining the uniformity of the cosmic microwave background, inflation theory offers a compelling solution. The CMB appears almost uniformly distributed across the sky, with extremely slight temperature differences. This uniformity, combined with the isotropy of the universe, uniformity in all directions, puzzled cosmologists before inflation theory. The universe is vast and light takes time to travel across it, so regions on opposite sides of what we can observe in the universe haven't had enough time since the Big Bang to exchange heat or light and reach the same temperature. This creates a problem called the horizon problem, especially when we see that the cosmic microwave background, CMB, is remarkably uniform. To solve this puzzle, scientists came up with inflation theory. They suggest that right after the Big Bang, there was a short period where the universe expanded rapidly. Inflation theory says that the observable universe went from being incredibly tiny to much larger in a fraction of a second. This means that parts of the universe that are now far apart were once close together before inflation pushed them apart. During this time, these regions were close enough to share energy and reach the same temperature. Then, as the universe expanded, this uniformity got stretched out. So, when we look at the CMB, we're seeing a picture of a much smaller universe that got stretched out as it expanded, which explains why it has a uniform temperature. The small variations in temperature we do see in the CMB are because of tiny fluctuations in the density of the universe just before inflation happened. These fluctuations got amplified during inflation and became the seeds for the large-scale structure of the universe, like galaxies and galaxy clusters. On a different note, antimatter is like a mirror image of matter, with opposite charges. For every particle of matter, there's a corresponding antiparticle of antimatter. For instance, the positron is the antiparticle of the electron, and it carries a positive charge. The antiproton is another example, having the same mass as a proton but a negative charge. This symmetry between matter and antimatter is fundamental in physics. In 1928, British physicist Paul Dirac made a groundbreaking prediction about the existence of antimatter while working on equations combining quantum mechanics and special relativity. His equations suggested the presence of particles with the same mass as electrons, but opposite charge. This prediction was confirmed in 1932 when Carl Anderson discovered the positron, the first evidence of antimatter, validating Dirac's theoretical framework. When a particle of matter meets its corresponding antiparticle, they annihilate each other, releasing energy in the form of gamma rays. This process showcases the equivalence of mass and energy, as famously described by Einstein's equation E equals mach squared, and is a fundamental aspect of how antimatter interacts with matter. Antimatter isn't just a theoretical concept, it has practical applications. For instance, in medicine, positron emission tomography, PT, scans rely on detecting gamma rays from positron annihilation to produce detailed body images. Moreover, studying antimatter is crucial for expanding our understanding of the universe. Cosmologists explore antimatter to tackle fundamental questions about the Big Bang and why our observable universe seems to be mostly made up of matter, despite theories suggesting equal amounts of matter and antimatter were produced in the early universe. Investigating antimatter also pushes the boundaries of particle physics. Scientists aim to create, trap, and study antiparticles in laboratory settings. Experiments with antihydrogen atoms, for instance, seek to compare their properties with regular hydrogen, testing the fundamental symmetries of nature. These studies could unveil new physics beyond the standard model, offering insights into the fundamental forces and particles that shape our universe. Let's delve into CP violation and its connection to the asymmetry between matter and antimatter. In particle physics, CP violation is a fundamental phenomenon where the combination of charge conjugation, C, and parity inversion, P, isn't preserved. Put simply, it means that certain processes involving the transformation of particles into their corresponding antiparticles don't behave the same way when charges and spatial orientations are reversed. Understanding CP violation is crucial for explaining why there's more matter than antimatter in the universe. In the early universe, matter and antimatter were created in nearly equal amounts. However, if all processes respected CP symmetry perfectly, they would have annihilated each other completely, leaving behind a universe without matter. The fact that we have more matter than antimatter suggests that there are processes where CP symmetry is violated, favoring the production of matter over antimatter. This violation allows for subtle differences in the behavior of particles and antiparticles, resulting in a slight excess of matter that led to the formation of structures in the universe. Experimental evidence of CP violation has been observed in rare decays of elementary particles like neutral kaons and B mesons. These experiments have provided crucial insights into the mechanisms behind the matter-antimatter asymmetry in the early universe. However, understanding the exact origins of CP violation and its link to the observed matter-antimatter disparity remains an active area of research in particle physics. Exploring the beginnings of the universe has fascinated thinkers across disciplines for centuries. Scientists, philosophers, and theologians have all pondered whether we can truly grasp how everything began. Through studying cosmology and particle physics, we've gained insights into the immense cosmic events that occurred billions of years ago. Despite our progress, the ultimate origin of the universe remains cloaked in mystery. The Big Bang Theory offers a valuable framework for understanding the universe's evolution from its earliest stages. However, as we probe closer to the moment of creation, we encounter a realm where our familiar laws of physics cease to apply. This realm is characterized by extreme conditions, unimaginable temperatures, densities, and energies that challenge our understanding. It's a place where even the fabric of space-time undergoes profound transformations. In our pursuit of understanding, we confront the limits of our human intellect and the boundaries of scientific exploration. Can we, with our finite minds and empirical methods, ever hope to fully grasp the mysteries of existence? Or are there aspects of reality that will forever elude our comprehension? Some argue that seeking understanding is an innate part of being human, driving us to explore and question the deepest mysteries. Others suggest that there are inherent limits to what we can know, and some truths may remain beyond our reach indefinitely. This debate underscores the complexity of our quest to comprehend the origins of the universe. The concept of nothing in modern physics challenges our core understanding of reality. It's not merely an absence of matter or energy as traditionally thought. Instead, in the world of modern physics, nothing is a dynamic realm governed by quantum mechanics. Even in what appears to be empty space, there's a flurry of activity known as vacuum fluctuations. These involve virtual particles spontaneously appearing and disappearing, borrowing energy from the vacuum before annihilating each other. Moreover, the idea of nothing is deeply connected to the origin of the universe. According to the Big Bang Theory, the universe began from a singularity, a point of infinite density and temperature. But what existed before this event? Was there truly nothing, or are there dimensions beyond our current understanding? Particle physics research, while seemingly abstract, has real-world applications that benefit society. One major area is in medical technology. Innovations stemming from particle physics research, such as PET and MRI, have revolutionized medical imaging, aiding in diagnoses and treatment plans for countless patients worldwide. Additionally, techniques like proton therapy, developed through particle physics research, offer more precise and less invasive options for treating cancer, improving outcomes for those undergoing treatment. Research in particle physics has played a pivotal role in creating innovative materials and technologies with wide-ranging applications. Take, for instance, the inception of the World Wide Web at CERN, aimed initially at enhancing communication among researchers, but now fundamentally altering how information is accessed and shared globally. Additionally, progress in particle detector technologies has resulted in the production of more sensitive detectors. These find use in various fields such as security screening, environmental monitoring, and archaeological exploration, enhancing our ability to understand and interact with the world around us. The pursuit of fundamental knowledge in particle physics frequently catalyzes advancements in other scientific realms. Collaborations across disciplines like physics, engineering, and mathematics drive interdisciplinary research, sparking innovation across different domains. Looking ahead, future breakthroughs in particle physics hold immense potential for transforming everyday life. While some of these advancements may appear distant or abstract, their societal impact could be profound. One significant area of promise is in energy production and storage. Innovations stemming from particle physics could lead to more efficient and sustainable energy sources, addressing critical issues like climate change and energy security. For instance, progress in fusion energy research, inspired by the study of plasma physics within particle accelerators, might eventually offer a clean and nearly limitless energy solution. Furthermore, discoveries in particle physics could drive advances in technology and computing. The emergence of quantum computing, drawing heavily from principles explored in particle physics, has the potential to revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Quantum computers could solve complex problems exponentially faster than classical computers, ushering in new frontiers for scientific exploration and innovation. Particle physics research, despite its potential for groundbreaking scientific progress, prompts careful ethical reflection on various fronts. Firstly, there's the matter of resource allocation. Particle physics experiments demand significant financial investment and access to advanced technology. Critics argue that these resources might be better directed toward addressing urgent societal needs like poverty, healthcare, and education. Conversely, proponents contend that investing in fundamental research can yield unexpected technological advancements and long-term societal gains. Safety is another ethical concern, especially regarding experiments involving high-energy particle accelerators. While the chances of catastrophic events are extremely low, some express apprehension about potential risks, such as the formation of micro-black holes or the emission of hazardous radiation. It's crucial for researchers and regulatory bodies to thoroughly assess and mitigate these risks to safeguard both experimenters and the public. The ethical implications extend to the dissemination of knowledge and the potential misuse of scientific discoveries. Particle physics research unveils valuable insights into the universe's workings with broad implications for technology, medicine, and beyond. However, there's a risk that this knowledge could be weaponized or exploited harmfully. Balancing the benefits of scientific progress with the imperative to prevent misuse requires careful consideration from scientists and policymakers alike. Moreover, ethical questions arise concerning international collaboration and the equitable distribution of research findings in particle physics. Collaborative endeavors among scientists from diverse nations drive progress in this field, yet issues like intellectual property rights, data sharing, and fair access to research opportunities can surface, particularly in contexts of limited resources or disparities between countries. Upholding principles of fairness and transparency in collaboration is vital for maintaining scientific integrity and fostering global advancement. Particle physics research has incredible potential for discovering new things and creating innovative technologies. But it also raises important ethical questions that we need to think about carefully. By discussing these questions openly, scientists, policymakers, and society can work together to deal with the ethical issues of particle physics research and make sure it benefits everyone. As we think about where particles come from, we're faced with big philosophical questions that go beyond just science. Maybe in the grand scheme of things, there's a deeper truth we haven't quite grasped yet, a truth about how everything in the universe is connected and how there's endless potential in everything around us. Could it be that particles don't just come from nowhere, but from the infinite possibilities that exist in the universe? This challenges us to think beyond what we already know and to embrace the endless possibilities that are out there. How do you think particles came to be? How did everything start? Leave a comment down below, and as always, thank you so much for watching yet another SpaceDrift documentary. Until next time, take care.